Section 11.3, derivatives by definition. What we're going to do is we're going to identify a derivative and find derivatives of functions by definition. So what we're going to start off with is try to figure out what this idea of what a derivative actually is. So the tangent line is the line that best approximates the slope of a graph at a certain point. But we know to be able to find the slope of a line we need 2 points, or at least we have in the past. So let's take a look here. So instead of starting with the tangent line, we're actually going to start with the secant line. The secant line is a line that intersects the graph at 2 points. So let's pick 2 points here, one here, and one here. And we're going to identify this secant line with some unknown values. We'll start with the point here on the bottom, and we'll identify this point as x. So now, if we move, we're going to say h units to the right, then the point on top would represent the x value plus that distance h. Well, to find the y value, we just plug that value in. So if I want to know what the y value is at this point, we would plug x into the function, and so the y value would be f of x, and then the point on the top would be f of x plus h. And so what is the slope of the secant line? Well, the slope of the secant line then, as we know, is the change of y over the change of x. So that would be f of x plus h minus f of x. I'm subtracting the y values of the 2 points. So f of x plus h minus f of x divided by x plus h minus x. This is the change of your x values. Well, you can see that the x's cancel out, so we can simplify this as f of x plus h minus f of x over h. So that would represent the slope of the secant line, a line that intersects the graph at 2 points. So once again, the slope of the secant line, as we have just described, is equal to the change of y, f of x plus h, minus f of x, divided by h. So we had a point here and a point here, and here was the secant line. What happens if we choose the point here, and we draw in another secant line? Or if we get a point here, and another secant line? And as we get closer to the point, what are we getting closer and closer to? We're getting closer and closer to the tangent line. What is happening to our h value? Originally, h was this distance, and then we did this point, and now it's that distance, and then this point, and this point. And so what was happening to the h value? H was getting closer and closer to that difference of 0. So as h approaches 0, the secant line approaches the tangent line. So what is the slope of the tangent line then? It's the limit as h approaches 0 of the slope of the secant line. Well, what does that mean? That would be the limit as h approaches 0 of the slope of the secant line from above, which is f of x plus h minus f of x divided by h. And that is the slope of a tangent line, which we're going to write as f prime of x, which is the derivative. Okay, so take a look at that again. The limit as h approaches 0 of f of x plus h minus f of x divided by h. That represents the derivative of that function, which is the slope of the tangent line. So here's what we just found out. The derivative of f at x is given by f prime of x. Once again, that's how it's read. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we are finding the slope of the tangent line at a given point. Now this is just the generic formula, so we will look at very specific functions and be able to find the derivative, but once again, remember, the derivatives is going to be the limit as h approaches 0 for that particular function. So let's go ahead and take a look at a couple examples. The first one is find the derivative of the function f of x equals 4x minus 1. So what are we going to do? Well, we are going to find the limit as h approaches 0. So this is f prime of x, that's the derivative we're looking for f of x plus h minus f of x divided by h. So here we go. F of x plus h. This right here. Wherever there's an x, we're going to plug x plus h. So we have the limit as h approaches 0 of 4 times x plus h minus 1. So this whole thing right here is f of x plus h minus f of x, which is the function 4x minus 1. All of that is divided by h. Now, if we're finding a limit, one of the things that we had talked about is to use direct substitution before we try to do anything. And if you look, if you try to plug in 0, you'll get f of x plus 0 minus f of x divided by 0. Well, that's just f of x minus f of x divided by 0, or 0 divided by 0. So direct substitution will not work on the derivative. You're going to have to simplify and get something to cancel. So let's go ahead and continue to simplify. So it'll be the limit as h approaches 0 of 4x plus 4h minus 1, distribute the negative sign, minus 4x plus 1 divided by h. Look what happens. 4x, negative 4x, negative 1, 1. All of that cancels. So we're equal to the limit as h approaches 0 of 4h divided by h. I still haven't canceled anything. And then right there you can see the h's are going to cancel, so you're still left with the limit as h approaches 0 of the function 4. Well, that's just a horizontal line. So as h approaches 0, what's the limit as h approaches 0 of the function 4? That would just be equal to 4. So the derivative of 4x minus 1 is equal to 4. Think about that. Doesn't that make sense? If the slope of the tangent line for that function is 4, well, it's a line. So isn't the slope of any point on that graph 4? So hopefully that kind of makes sense in terms of what you're looking for. Don't forget what it is we're trying to find. We're trying to find the slope of the tangent line at any given point on that graph. At any given point, the slope will always be 4 on a line. So pause the video. I'm going to work through this one. I want you to try to work through this one just as well. It's very similar to the example 1 we did, 4x minus 1. This is 1 minus 3x. So find the derivative of the function f of x equals 1 minus 3x. Alright, so we did the limit as h approaches 0, once again, of f of x plus h minus f of x divided by h. Remember, that is the difference quotient, which has to do with that slope. So we plugged in x plus h wherever there was an x. So we replaced this x with this x plus h, which is right there. And then we distributed, and then we subtracted the f of x also. Simplified, had some things cancel out. Negative 3 h divided by h. Canceled the h's. Now we're looking for the limit as h approaches 0 of the function negative 3, which once again is just a horizontal line. And that would be approaching negative 3. Still makes sense though, because the slope of the linear equation is negative 3. So any point on that graph should have a slope of negative 3. Alright, we're going to continue to look at some different functions here the rest of the way. Find the derivative of the quadratic f of x equals x squared plus x. So the derivative is equal to f of x plus h, and you're going to see me consistently write this first before I start plugging anything in. And I messed up because I didn't put the limit. So the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is the limit as h approaches 0. Wherever there's an x, we're going to plug in x plus h. So that's here and here. So that'll be x plus h squared plus x plus h. So that's f of x plus h, and then minus the function x squared plus x. And then that's all divided by h. So the limit as h approaches 0, we're going to simplify this. X plus h squared is x squared. And it's not just h squared, it's x squared plus 2xh. Remember, there's that middle term, plus h squared, plus x, plus h, minus x squared, minus x. We're distributing that negative sign, divided by h. So what cancels? X squareds, x's, and it looks like that's it. So we have the limit as h approaches 0 of 2xh plus h squared plus h divided by h. Well, we can't do direct substitution. We haven't canceled anything. So you will notice that there is a factor of h that can be canceled, or that can be factored out from the numerator. And make sure it's 2x plus h plus 1. When you factor an h out from h divided by h is 1. Now you can see that the h's cancel. And so you're left with the limit as h approaches 0 of 2x plus h plus 1. And then I will do my direct substitution. So 2x plus 0 plus 1 is equal to 2x plus 1. So the derivative, f prime of x, the derivative is a limit. So we've already answered the limit question, so we shouldn't be writing limit anymore. It's equal to the expression 2x plus 1. Now you might be thinking, well, how's that the slope of the tangent line? Well, remember, we don't know what point of this quadratic we're looking at. We can look at any point on the quadratic. So this is the slope formula for that particular function. We'll talk more about what the slope is at a particular point, but the derivative helps us find what that is, and that's the expression 2x plus 1. So we've looked at linear, we've looked at quadratic. Now this one is constant. So when you go to figure out this one, it's a little strange, but you'll notice the limit as h approaches 0 of, once again, f of x plus h minus f of x divided by h. We have the limit as h approaches 0, and then f of x plus h. Well, there's no x to plug it into. So f of x plus h is just 5. So that represents f of x plus h. And then minus f of x, which is also just 5. This is a horizontal line, so it doesn't matter what point you pick. The y value is going to be 5 divided by h. So that'll leave us with the limit as h approaches 0 of 0 divided by h. Well, 0 divided by h is 0, but as in terms of as h approaches 0, what is it getting closer and closer to? Well, it's getting closer and closer to 0. So the limit as h approaches 0 of, once again, that 0 value is equal to 0. So we have f prime of x is equal to 0. All right? And once again, think about that. That's the slope of the tangent line. What is the slope of this function that's a horizontal line? The slope was always going to be 0. So it makes sense that the derivative is 0. All right, let's take a look at a rational function now. So continue to set it up the same way as all the other ones. F prime of x, that's the derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So because this is a rational expression, we're going to get some fractions within fractions, but we'll fix that. So 1 divided by x, we're going to replace x with x plus h. So 1 divided by x plus h minus the function f of x divided by h. So just as we had done earlier on, we're going to simplify this by multiplying by our common denominator. So we're going to multiply this whole top by x times x plus h, and then if we do it in the numerator, we got to do it in the denominator, and that's that common denominator. So that'll leave us with the limit as h approaches 0, and we're going to distribute this. So this whole thing is going to get distributed to this one and this one. So the x plus h cancels, which leaves us with 1 times x, which is just x. The x cancels, and that leaves us with minus, make sure it's the quantity of x plus h. And then on bottom you have an h times an x times an x plus h. So don't distribute that, we're going to have to cancel something. So let's see what we have here. Limit as h approaches 0 of x minus x is going to cancel, but then you're going to get a negative h on top because you have to distribute the negative over h times x plus h. So now you can see that the h's are going to cancel. So you have the limit as h approaches 0 of negative 1 divided by x times x plus h. And now we can use our direct substitution since our factor canceled, and we will plug 0 in wherever there's an h, and that'll give us negative 1 times x, which is x squared. So the derivative of the function f of x is equal to negative 1 over x squared. So there's a rational function for you. And the last function we're going to look at is a square root function. So we have, once again, the derivative of f of x, f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So what do we have here? We have the limit as h approaches 0, so wherever there's an x, we're going to replace with x plus h minus f of x divided by h. So hopefully what you realize is we're not going to cancel anything by factoring or simplifying. We're going to have to multiply by the conjugate, which we've done earlier. So we'll multiply by x plus h minus, actually plus, the square root of x and so then we'll have the limit as h approaches 0 of x plus h minus x, remember the conjugate, middle term cancels, and then we're going to leave this on the bottom in factored form. So you see the x's are going to cancel. That'll leave us with the limit as h approaches 0 of h over h divided by h times the quantity x plus h, and then you'll see the h's cancel. And so once the h's cancel, we're left with the limit as h approaches 0 of 1 divided by the square root of x plus h plus the square root of x. We do our direct substitution, and we get the square root of x plus the square root of x on bottom, which is 1 over 2 square roots of x. And we're not going to rationalize or anything else, so that will be our final answer. The derivative, f prime of x, of the function f of x is equal to 1 over 2 square roots of x. So I was able to show you a lot of different functions: linear, quadratic, rational, constant, the square root function. So we can find the derivative by using definition of all these different functions. If you want to challenge yourself a little bit, you could ask yourself y equals mx plus b. If I take the general form of a linear equation, can I find the general form of the derivative of a linear equation? You could do the same thing with potentially a quadratic, ax squared plus bx plus c. So you could actually take the general form of some different functions and find the derivative of each of those individually, and that'll give you an idea as to what some of these rules are that we will talk about later on as well.